And when one approaches two, they combine and they're bonding. Thus hydrogen as a rule is found in nature as H2 energy can be.
Hi everyone, welcome to the very last Thursday Friday video lesson of 2020. Today in class we learned about molecular shapes and polarity. So to start off our warm-up, we had one of my favorite warm-ups of the year. So I want you to imagine that I give you 100 $1 bills. The catch, there is a catch, there's always a catch, is that you have to share it with another person. Now in class I just said whoever is next to you in your Zoom window, skipping me. And you have to share it. You can't keep all of it. Let's do, full dollar amounts. How much would you keep for yourself? How much would you give to your partner? Well, most students usually go 50-50. You guys are really, really nice. But we get some interesting answers too, like 55-45, 60-40, 99-1. That one comes up a lot as well. 90-10, 80-20. We cut it up in different ways. We share that money, but we share it differently. This is very much like bonding, because when I've got a covalent bond, they're sharing electrons, but they're not always sharing them equally. And we're going to circle back to this in a little bit when we start talking about polarity. Your homework is to finish your molecular shape POGL. Remember, you were supposed to have gotten pages 1 through 3 finished by class today, but you can finish the rest over the weekend. There's only about 3 more pages left. Really, it's kind of closer to 2 because most of one page is just a reference table. So you need to finish up that POGL. Then in class, I unlocked the model lab. It's a lab. It's also kind of a quiz. And you know how that works. I will give you a second attempt. However, I'm not unlocking attempt number 2 on Friday. Attempt number 2 is going to be locked during class on Monday and Tuesday. So you'll get a second attempt, but not until class time. And then I just want to remind everyone, if you haven't already gotten an A on your Lewis dot structure and covalent naming quiz, you have a second attempt on that test. There's no reason you should settle for a B or a C on your first attempt. Come in, see me during office hours, find out what you did wrong, and then take it again. You'll get a better grade. So after our warm-up, we went right back into our Unit 4 notes. So we started taking some notes on molecular shapes. Then we started talking about molecular polarity. Then the rest of class, we had a little bit of free time. You could continue working on your POGL, making sure you got that in, or you could start on your model lab if you already finished your POGL. A few kids already did. I also want to point out that on our Canvas module, there's another optional assignment. It's not worth any points, so if you don't do it, you're fine. It's there as an option. I even made the due date January 26th, the very last day of the semester, so you won't be scared seeing that there's a assignment past due that you forgot about. So you need to log into your Gizmo account. If you've forgotten your Gizmo login, just ask me. I can look it up for you. When you go to the website, explorelearning.com, log in, you'll see that there's a new Gizmo that you can work with. Polarity and intermolecular forces. So if you launch your Gizmo, you'll want to go to molecular polarity, and you can look at polar compounds and see what those look like compared to non-polar compounds. You can look at valence electrons, not look at valence electrons, turn on electrical fields, see what happens. You can get some hands-on experience with molecular polarity. See which ones are polar, which ones are non-polar. Although from our notes, I did say let's pretend like all of our bonds are polar unless it's the same thing. So really you'll just want to play with these polar bonds. Some of these make polar molecules, some of these make non-polar molecules. It's a great way to get some hands-on experience. And then in that assignment, I've made a CAMI document. This is the assignment that I used to give when we did this in class last year. So the whole point of these Gizmo assignments is that they lead you through the experience, so it helps you find the information it wants you to experience. So it's a good idea if you just aren't quite getting it and you want some more practice with it. But again, this is completely optional. I just wanted to give you an option so you could get some more practice so you could see how it works with other things in the world. So once you opened up your Unit 4 notes, Part 3, we skip down to slide 10. We're skipping slide 9. You don't need to worry about it. If you have questions, please, I fully support and I fully encourage you to come and see me during my office hours. I would love to talk about octet exceptions. I actually think they're really kind of fun and neat. But we're skipping that for now, and we're going to slide 10, determining the shape of different molecules. So we're using the VSEPR theory, which stands for valence shell electron pair repulsion. So remember, my electrons all have the same charge. They want to get away from each other, like charges repel each other. Right here, I've got an image of a woman walking away from a man who is not wearing his mask. If you go into a store somewhere and you see a person without a mask, you are repulsed. You try to put a distance between you and them. Another way that I've been talking about this a lot is the stinky person on the bus. If you get on a bus and that front row is a really smelly person, you don't want to sit next to that really smelly person. You're going to sit as far away from them as possible because you want to be as far away from that smell as possible. So you're probably going to sit all the way in the back of the bus. So if I know that people don't want to sit next to stinky people, and I know I've got 2 people on a bus, and I just assume all people are stinky, I know where those people are going to sit on the bus. They're going to sit as far away apart as possible. So since I know that my electrons want to space out as far apart as possible, I can predict what shape they're going to be. Because remember, what links my atoms together are shared electrons. So those shared electrons between 2 atoms want to be as far away as they can be from the other 2 atoms. They're going to spread out. So I know how they spread out. I can guess what shapes they can make because it all depends on how many things need to spread out from each other. So in order for me to figure out what the shape is, it all depends on how many domains around my central atom. Now, one domain can be a lone pair of electrons, so 2 dots. It can also be a single bond, so a single line between 2 atoms, or a double or triple. So if I have a double bond between 2 atoms, so if I've got 2 lines between a carbon and an oxygen, that's one domain because I've got one thing hanging off that carbon, which is an oxygen. So even though it's a double bond, it's still just one domain. Same with triple bonds. A triple bond, so 3 lines, counts as one domain coming off of my central atom. Now, there's 2 more phrases that we use a bit, electron geometry and molecular geometry. Electron geometry is just how many domains I have total. Sometimes we look at electron geometry versus molecular shape. We're not going to compare the 2, not really, because my shape is sometimes the same as my electron geometry, but my molecular shape actually depends on how many of my domains are bonded or lone pairs. That's the really interesting stuff. That's what I want you to focus on. So in your PhET lab, there was some talk about electron geometry. You don't have to worry about it too much. All we really care about is molecular geometry. That's the shape of our molecules. So after talking all of this about domains, I want to give us some practice. So in class, we went over some practice problems. In order to figure out shapes, you need to be able to do Lewis dot structures. In your model lab, we give you the Lewis structure you need, and then you have to be able to determine from that structure what's the shape going to be. So we had some practice here counting domains. So here I have CH2F2. I have 1, 2, 3, 4 domains around my carbon. I have 4 things hanging off my central carbon. Each time I have something on my central carbon, it's a bonded pair. So I have 4 domains of bonded electrons, and I have no lone pairs on my central atom. I don't care about those lone pairs on that fluorine. All I am looking for our shapes is what's happening to my central atom. Then here I've got SO2. I have 1, 2, 3 domains around my central atom. I have 3 things hanging off my sulfur. I have 2 oxygens and 1 lone pair. So I've got 3 domains. I have 2 domains are bonded pairs. I've got sulfur to oxygen, that's 1 bonded domain, and then sulfur to oxygen, that's my second domain of bonded electrons. And then I've got 2 dots on top of my sulfur, so that's 1 pair. So I have 1 domain that's just a pair of electrons. Then my last one, I've got H2O. I have 4 things hanging off my oxygen. I have 1, 2 hydrogens, then 1, 2 lone pairs. So I have a total of 4 things hanging off. 2 of my domains are bonded electrons, and 2 of my domains are lone pairs. That's how we count our domains. So now we've got some practice on counting domains and figuring out if they're bonded or lone pairs. Now we can apply it to our shapes. Now, the first thing I want to note here is that all of these shapes in this table have at least 3 atoms in the molecule. If I only have 2 atoms, there's only one possible shape I can make, no matter how many domains or lone pairs I have. If I only have 2 different atoms, I can only make a straight line. So if I have only 2 atoms, it's always linear. Once I get to 3 or more atoms total, now it gets interesting. So my first shape is if I only have 2 domains around my central atom. So if I have 2 things, it's going to spread out as far as possible. So I have here my carbon dioxide. I have my 2 oxygens as far apart from each other as they possibly can get. They're on opposite sides of my carbon. So that's a 180-degree distance between them. So I've got 2 regions of bonded electrons. I don't have any lone pairs. This is called linear. And notice, if I had any lone pairs there, I would have to lose one of my bonded, and then I would be down to just 2 atoms. So that would automatically be linear there as well. Next, I have 3 domains. So if I have 3 things and they're going to separate out equally, 3 regions, my bond angle is now 120 degrees. So if they are all bonded domains and no lone pairs, it looks like this. This is called trigonal planar. It's kind of like a triangle, and it's a very flat shape. It's all in one plane, hence planar. Now, if I take off one of these, and I replaced one of those bonded electrons with an electron cloud or a lone pair, I now have a new shape. I don't put my electrons, my lone pairs, in the shape. My lone pairs are here, but they're kind of invisible. I don't see them. But they do affect everything else. It is electron domain, so it pushes those other 2 down. These would like to be 180 degrees apart. That would make them further apart from each other, but they can't because I've got an electron pair right here. So I keep that same 120-degree angle between them, but it's a new shape. It's not a triangle anymore. Now it looks like I took a straight line and I bent it. This is bent 120. So it's bent with an angle of 120 degrees. There are 2 different bents. And so the name bent is never the answer. I always want to know if it's bent 120 or if it's bent 109.5. So next we have a total of 4 domains. So if I have 4 domains, I want to space everything out as equally as possible. My bond angle is 109.5 degrees. Now, a lot of students, they are only thinking 2 dimensions. They think right angles, 90 degrees, but this is 3 dimensions. We're just not used to it, but it looks like this. Sometimes it's called the tripod, but my official name for it is tetrahedral. It has 4 faces, 4 sides to it. It's like a little pyramid, a 3-sided pyramid and its base. So this is tetrahedral. I've got 4 domains, and each of those domains has a bonded pair in them. Now, if I take away one bonded pair and replace it with a lone pair, I have a new shape. This is trigonal pyramidal or trigonal pyramidal. So it looks, if I hold it just right, it looks a lot like trigonal planar, but it is not trigonal planar because it's not on one plane. It actually stands up on its own like a little pyramid. So trigonal pyramidal has one lone pair that's kind of invisible. Well, it is invisible, but you can see its effect. It's pushing all the others down. They would like to be spread out like trigonal planar, but they can't because they're being pushed down by the stinkiness of the electrons on top. And then if I take away another bonded pair and replace it with another lone pair, I get my last shape. Again, it looks a lot like a straight line that someone took and bent. So this is bent 109.5. It's my second bent. I've got two invisible lone pairs here pushing those other bonded pairs down. They all take up their own space. Remember, electrons are stinky. Even though I can't see them, they can be smelled, and they're pushing the others. So now that we've talked about shapes, we can start talking about the polarity of those molecules. So, circling back to our warm-up, remember you shared those $100 with another person, but most of us didn't share it equally. That's what happens between a lot of our atoms. Now, sometimes they do share it equally, and most of the time it's not. We used to have you calculate just how unequally they actually shared it. We give you a table of all the electronegativity values and you'd find the differences. But this year we're going to keep it pretty simple unless it's the same atom that it's bonded to. So like oxygen to oxygen, then you assume the bond is polar. So oxygen and oxygen, it's the same atom. Neither is going to pull harder than the other. But if I have carbon and fluorine or carbon and nitrogen, those all have different electronegativity values. So they're going to have a difference. One's going to pull stronger than the other. You don't need to worry about the electronegativity values. I'm not going to have you calculate them. Just know that every element has a slightly different value. So, because they have slightly different electronegativity values, sometimes some elements are better at pulling those electrons towards them when they're sharing them. It's kind of like, imagine you have two friends. You're an electron, you've got two friends who are two different atoms. Friend on your left side, they have the brand new PS5, a home theater, a panini press, popcorn machine, fountain sodas. You're going to spend a lot of time at that friend's house after school. But your other friend on the other side of your house, great friend, one of your best friends, they've got a lot of jigsaw puzzles. Jigsaw puzzles are fun. You will spend time with that friend as well. But you're probably spending more time with your PS5 friend right now. So you get shared, you go to both of their houses, but you tend to go to one house more often. And this is legitimately what's happening to those electrons. Those electrons are over at each atom, but they hang out at one of those atoms more than the other. And whenever that happens, the bond itself is polar. So my molecules are made up of atoms who have bonds holding them together, and those non-equal sharing bonds, those polar bonds, can help make an entire molecule polar. But it's not just down to those bonds themselves. I need to look at the whole shape. So assume that all of your bonds are always polar. They're pulling your atoms away or towards the central atom. It doesn't matter who's pulling more or less, just know that they're all just pulling. And every time you have two different elements attached, they pull different amounts. Again, it doesn't matter who pulls more or who pulls less, they're pulling different amounts. So, if I have a polar molecule, I'm being pulled more in one direction than the other direction. If I have a nonpolar molecule, I'm not being pulled in any direction whatsoever. They cancel out. Or if I have the same atom attached to itself, So an oxygen to an oxygen, there's no difference. So here I've got two examples. I've got water and I've got carbon dioxide. So here in my water, I have hydrogen to oxygen, and my electrons are actually being pulled towards the oxygen. And then I've got lone pairs. Lone pairs don't pull at all. So whatever is happening between my oxygen and my hydrogen can't be canceled out because they're not equal and opposite angles. So this is a very polar molecule. But if I look over here at my carbon dioxide, I'm getting pulled in equal and opposite directions. It doesn't really matter that I'm getting pulled to the oxygen. I could just as easily be pulled towards the carbon. But what's important here is they're evenly spaced out. So if I get pulled to the right oxygen, I'm getting pulled the same amount to the left oxygen. I'm getting pulled in equal and opposite directions, so I'm not getting pulled to the left or the right. Here, I've got my arrows going up and over, so this one's getting pulled up and to the right. This one is getting pulled up and to the left. So the left and the right cancel, but the up and the up add together. Now, you don't have to draw these. There are some other ways you can easily figure out if these dipoles, or the directions that the electrons are being pulled, cancel or don't cancel. My first rule here is that lone pairs always make your compound polar. So, if you are looking at a molecule, the first question is, are there different elements? So if you have something like O2 or O3, they're all the same element, so it's nonpolar. O2 does have lone pairs, but since it's all the same element, or O3, it's not a polar compound. Those bonds, I'm not getting pulled more towards this oxygen or that oxygen, this oxygen or that oxygen, so those are nonpolar. But if you have different elements, so you have a central atom and you have other atoms outside, you need to ask if it is symmetrical. If it is not symmetrical, then it is polar. If it is symmetrical, then it is nonpolar. So my example here for a polar molecule is CH2F2. Now, I draw the Lewis structure here. You might say, but Miss Brubaker, that looks very symmetrical. You've got hydrogen on the top and the bottom, fluorine on the left and the right. You can easily cut that in half and fold it on itself. And it looks that way in 2 dimensions. But when I have it in 3 dimensions, you see there's something else going on. No matter how I rearrange this, I'm always going to have a fluorine side and a hydrogen side. That's not symmetrical. It doesn't matter what the electronegativity difference is, but I'm getting pulled in equal and opposite directions, but not equal and opposite amounts. Whatever the difference between carbon and fluorine is going to be very different from the difference between carbon and hydrogen. So although I'm being pulled in equal and opposite directions, I'm not being canceled out. I'm being pulled by different amounts. So this would be a very polar compound. Now compare it to this one. Now I have CH4. I have the same element on all sides of my carbon. So I'm getting pulled in equal and opposite directions. So this is a nonpolar compound. Any amount that I'm getting pulled up, all 3 of these would add up to cancel it out to the down. So they all cancel each other out. So it's not polar. I have the same thing and it's all equally spaced out. So I've also given you a little guide about what shapes can be symmetrical compared to which shapes can never be symmetrical. Linear, trigonal planar, and tetrahedral can be symmetrical. Both my CH2F2 and my CH4 are both tetrahedral shapes. So this one was symmetrical, it is nonpolar, but my CF2H2 is not. It's not symmetrical, so it is polar. So the 4 shapes that can be symmetrical are linear, trigonal planar, and tetrahedral. Now the other 3 shapes always have lone pairs on them, at least one lone pair, sometimes more. So because they have lone pairs, they can't be symmetrical. They will always be polar. So bent 120, bent 109.5, and trigonal pyramidal will always be polar compounds. So with those notes, you should be able to finish your POGL and you should be able to work on that model lab quiz. Now, I would like to point out there is an embedded video in your Unit 4 notes. It goes over how to determine which Lewis structures are polar or nonpolar shapes. Just another way to explain this. I think you might find it helpful. And there's also the very optional practice assignment in our module. Again, it's not for any points, but it gives you a chance to just see it more, see it in 3 dimensions, see how it interacts with other things. Okay. Well, I hope everyone has a safe weekend and I hope you all make good choices. See you on Monday and Tuesday.